नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। This is the 25th day of JEE Mains revision series. Today we are going to cover boron family part 1. Though this topic is going for the revision of JEE Mains, but it is equally important for JEE Advanced. So it's my suggestion that you can see this lecture for the preparation of JEE Mains as well as JEE Advanced. जिन लोगों ने हमारा चैनल सब्सक्राइब नहीं किया है उनसे हमें अनुरोध है कि वो हमारा चैनल सब्सक्राइब करें और अपने दोस्तों में शेयर करें ताकि हम अधिक से अधिक लोगों तक पहुंच पाएं। थैंक यू।
So in boron family part 1, first we are going to discuss the general properties of 13th group element. So the first property is atomic size. So as we move down the group in boron family, since the orbit number is increasing, it is expected that as we move down, the size of atoms should increase. So if we say that, what is the expected order? So boron should have the least atomic size and thallium should have the most atomic size. And if we move from left to right or up to down, it is expected that it is going to be continuously increase. But from experiment, the actual order is there is change in the position of boron and gallium. The atomic radius of aluminium is greater than that of gallium. So this exchange can be explained because when we write the electronic configuration for boron, we know that can be written as helium 2s2 2p1. For aluminium, I can write that this is equal to neon 3s2 3p1. And same way, when we are writing that what is the electronic configuration for gallium, first time the electron will be filled in 3D orbital, right? So if I'm writing what is the electronic configuration, it should be argon 3D10 4s2 4p1. So here in case of gallium, while filling the electron in outermost shell, before that there are 10 electrons in 3D and the screening effect of 3D electrons is less. So we can explain this order. We can say that in presence of 10D electrons, the force of attraction between the nucleus and the outermost electron in case of gallium is going to increase because of poor shielding effect of D. And because of that, we can say that the size of gallium is less than that of aluminium, right? So the presence of 10 D electrons offer only poor screening effect for the outer electrons from the increased nuclear charge in gallium. Now, this is a data from NCERT. They have given the radius in picometer, right? So this is the order. You can see here that the aluminium has an atomic radius of 143, which is greater than 135. So except this, if we are moving from top to bottom, the atomic radius is going to increase. The second property is general property for this group is melting point, and there is no fixed or regular behavior of melting point. So if you see here, elements with their melting point is given. So boron has the highest melting point of 2118 and gallium has the lowest melting point. If you put gallium on your hand, since its melting point is 30 degrees Celsius, our body temperature is 37 degrees Celsius. On room temperature is 25. So at room temperature, gallium is a solid. But if you put the gallium on your hand, your body temperature is 37. So it will melt because its melting point is 30 degrees Celsius. So what we have to remember in melting point, that boron has highest melting point in its group and gallium has lowest melting point in its group. Gallium has lowest melting point can be explained by the structure. Gallium exists as discrete diatomic molecule rather than a metallic structure, because we know that boron is non-metal and the other elements of this group are metal. So in gallium, there is a peculiar structure, metallic structure. In place of metallic structure, it is existing in the form of discrete diatomic molecules. And because of this unusual structure, the density in solid state of gallium is less than that of liquid state. Like we know about water, that water in solid state has less density than water in liquid state. Same for gallium. Gallium in solid state has less density than that in liquid states, and this is because of its unusual structure where it exists as discrete diatomic molecules. So this boiling point is not very important for us. The third property is ionization energy. Since we know that as we move down the group, the size of the atom should increase, and because of increase in size, we can say that the ionization energy should decrease as we move down the group. So it is expected that since boron is a non-metal and it is the smallest in size, the ionization energy for boron should be large. And as we move down the group, others are metals. So as we move down the groups, the ionization energy should decrease. So expected order is that boron, then aluminium, then gallium, indium, and thallium. This is the expected order for ionization energy. But from experiment, the order is very different what we are expecting. So this order can be remembered, right? I'm not saying that it is logically explained. We are doing experiment and find this is the actual order. Now in order to remember this, we are giving some logic that make a W, right? At the corner of each W there is an atom, right? Here boron, then this is increasing order of atomic mass. So boron, aluminium, gallium, indium, and thallium. Now what I am doing that in this W, if I pull this right hand side leg of W in downward direction, a little pull in downward direction here, right? Little pull, right? So now if whatever the W this is formed, at each corner there is one atom, right? Here boron, then here aluminium, gallium, indium, and thallium, and that will explain the order. You can check here that boron will come in the order you can match: boron, then thallium, then gallium, then aluminium, and indium. So we can say that the ionization energy of indium is minimum in boron family, and the ionization energy of boron is maximum. Now we can explain that why the ionization energy is decreasing from boron to aluminium, because as we move down, the aluminium has more size than that of boron. Boron is a non-metal, aluminium is a metal. So we can say that ionization energy should decrease due to increase in size. But why the ionization energy from aluminium to gallium is increasing, we can explain that in gallium, first time 10 electrons will come in 3D, right? And the screening effect of 3D electrons are less. So aluminium to gallium ionization enthalpy is increasing due to less screening effect of 10D electrons in case of gallium. Again, here it is unexpected. It should go down, but it is going up, right? So why the ionization energy is increasing from indium to thallium? That can be explained again by due to less screening effect of 4f electrons, because you know that in case of thallium, right, we fill electrons in F orbital, 4f orbital first time, I think, in case of thallium. And because of that, there is a lanthanide contraction, or we can say that a screening effect of F electrons are less. So the force of attraction between nucleus and outermost electrons is going to increase. So this is expected, right? But this is unexpected, explained by less screening effect of 10D electrons. This is expected, this is unexpected, so that can be explained by less screening effect of 14f electrons. So hope that you remember this peculiar order by remembering this W and pulling the right hand leg of W by small amount, and each corner has one atom. So by that method we can remember this peculiar order of ionization enthalpy. The fourth property is oxidation state. And for p block element, oxidation state means valence electrons. Group oxidation state means the number of valence electrons in that p block family. So here, when we are talking about boron, the outermost electronic configuration is ns2 np1. So there are 3 electrons in valence orbit. So we can say that the oxidation state of this family is +3. All shows +3 oxidation state. Group of oxidation state is +3. In case of gallium, indium, and thallium, besides +3 oxidation state also exhibit +1 oxidation state, right? So these three elements, beside +3, they can also exhibit. There are compounds of gallium, indium, and thallium where it is existing in +1 oxidation state. In gallium and indium, when we are talking about among these three, we are talking the first two, gallium and indium. +1 oxidation state is less stable than +3 oxidation state. But for thallium, +1 oxidation state is more stable than +3 oxidation state, which we are going to discuss with the help of inert pair effect. Gallium is apparently divalent in GaCl2. Sometimes GaCl2, where we are finding that the average oxidation in number of gallium is +2, but that is not correct. Actually, the structure of this is apparent. The actual structure of GaCl2 should be Ga plus GaCl4 minus. So this gallium is in +1 and this gallium is existing in +3 oxidation state. So be careful. GaCl2, this is average oxidation number will be +2. Otherwise, gallium exists in +1 and +3 oxidation state. So the fifth property is inert pair effect, and this inert pair effect is observed in heavy elements of p block. So what is the meaning of inert pair effect? We are going to learn. So the s electron pair in the valence shell of elements from thallium to bismuth appear to be comparatively inert in chemical reaction. Though this inert pair effect, we can say that from boron family to radon family, in all cases inert pair effect can be there, but it is more dominant in first three groups, that boron family, carbon family, and nitrogen family. That's why we are discussing that. So here, when we are writing the electronic configuration, in general, we can write that is equal to NS2 and NP, that is variable. In case of boron family, that will be 1. In case of carbon, that will be 2. In case of nitrogen, that will be 3. So in outermost shell, this NS electrons will not participate. So they are behaving like inert. So in inert pair effect, we can say that the common oxidation state -2 will be observed in case of inert pair effect. So when we are discussing about this thallium, lead, and bismuth, which is the thallium, lead, and bismuth, apart from radioactive or artificial element, these are the natural elements, and this is the heaviest element in their group. So all these three will show inert pair effect. Thallium +1 compounds are more stable than thallium +3 compounds. Tin +2, tin, if we discuss about carbon family, carbon, silicon, germanium, tin, and lead. So lead is the heaviest element, so it will show inert pair effect. Tin is before that. So tin can form tin +4. So +4 is the common oxidation state of carbon family. So tin +2 is reducing agent, means tin can convert into +4 oxidation state, but lead in +4 oxidation state is unstable, or we'll say that lead +2 is stable because of inert pair effect. Same way, antimony is of nitrogen family, and it is the last stable element of this is bismuth, right? So bismuth +3 is stable, but antimony is reducing agent, means antimony can convert it into antimony +5. So +5 oxidation state of antimony is stable, while +3 oxidation state of bismuth is stable. Bismuth is the heaviest element in this group, so its low oxidation number is stable, right? And its oxidation number of the group is 5. So 5 - 2 will be 3, is stable. Now, this is given in JDL, and this is very important. You can understand this very logically. The inert pair effect is not the explanation. Inert pair effect may we are saying that the NS electrons being inert, they are not participating in reaction. So we are just saying that what is happening, but it is not the explanation of why monovalency occur in group 13, why thallium is existing in +1, not in +3, why monovalency is not The reason is that they do not participate in bonding because of energy. If they will participate in bonding, right? So energy for that is required. If energy is not sufficient, they will remain inert. They will exist in the form of pair. So the actual reason is energy. And the phenomena we are saying is that inert pair effect because the electrons are not participating in bonding. The sixth property is about the oxide. So when we discuss about the oxide, B2O3 is known as boron sesquioxide, right? Sesqui means 1.5, means for one boron atom, if there is 1.5 oxygen atom, then we'll say that this is boron sesquioxide, and this is the structure of boron sesquioxide. And this is used in borax bead test. This is used in bead test where B2O3 is a colorless solid. And when a colored ion of metal will come, it will give that color of that metal ion, right? So borax bead test, we are using this B2O3. So Al2O3 and Ga2O3, gallium oxide and aluminium oxides are amphoteric. B2O3 is acidic oxide, and indium and thallium oxide. Now thallium oxide +3 and +1 both are basic. So indium and thallium oxides are basic. Gallium and aluminium oxides are amphoteric, and boron oxide is acidic in nature. So there is a question in JEE Advanced. I think they can ask this question because we are studying about Al2O3. This Al2O3 is also known as corundum. So in solid state, we can say that this is HCP with respect to, they can ask a question that what is the coordination number of aluminium +3 and oxide ion in Al2O3. So we should remember about the crystalline structure of Al2O3. It is HCP with respect to oxide ion, and aluminium +3 ion is present in octahedral void. Once we know that aluminium is present in octahedral void, means coordination number of aluminium is +6. And in order to calculate the coordination number of oxygen in binary solid, we can write that coordination number of cation upon coordination number of anion is equal to number of anions upon number of cations. So in a line, I can say that the ratio of coordination number is reverse of ratio of ions. So in this solid, you can write that in case of Al2O3, if I write the number of anions is 3 and number of cation is 2. And we know that what is the coordination number of cation? It is existing in octahedral void. So coordination number of cation is 6. So from here, I can calculate that what is coordination number of anion. So 6 multiplied by 2 by 3. So if I simplify, the coordination number of oxide ion is equal to 4. Hydroxides of boron family. So the first is boric acid, BOS thrice. So it is not hydroxide. Basically, it is an acid. But aluminium hydroxide and gallium hydroxide is amphoteric in nature, and indium and thallium hydroxide is basic in nature. When we are discussing about boric acid, it is a monobasic weak acid, because when we write the reaction of boric acid, when boric acid is added to water, it is a Lewis acid. It is electrodeficient. So what will happen, that it will accept lone pair from water molecule in its vacant p orbital, and there is formation of BOH4 minus. And here there is, because this water molecule is giving one OH minus, so in water H plus, water is now given OH minus, so what is left in water, that is H plus. So when something is added to water and it is increasing H plus in water, then it is an acid, and it is except one lone pair of electron or one OH minus, then we are saying that its basicity is equal to 1. But it is not a monoprotic acid. It cannot give H plus ion. It can accept OH minus ion. It's a Lewis acid. So it can accept one OH minus ion. That's why its basicity is equal to 1. Amphoteric means they can react anything, acidic oxide or whatever, this hydroxide or oxides are amphoteric, means they can react with acid as well as base. So aluminium hydroxide can react with HCl, aluminium hydroxide can react with NaOH, both is possible, right? We know that when aluminium hydroxide is going to react with HCl, there is formation of AlCl3 plus H2O. And we can write here that there is 3 molecules of this and 3 molecules of water will form. So this is the reaction. Again, we'll write that AlOH thrice will react with NaOH. When it will react with NaOH, again, it is acting. This is base and this is acid, and this is acting like a Lewis acid. It will accept one OH minus from here, and there is a formation of NaAlOH4. Right? So acid and base will react to form Lewis acid base adduct, which on heating, if you heat this, what will happen that this water will go outside and there is formation of NaAlO2. So if you remove here, there is formation of 2 water molecules. So water molecule will go in form of gas and this solid residue will be left. So you should know about this reaction, right? Now the 8th properties about halides, right? So when we are discussing about halides, Lewis acid behavior we are going to discuss, right? So in case of boron halides, when we are moving from fluorine to chlorine to bromine to iodine, the Lewis acid strength is increasing in this order. And we can explain this Lewis acid strength for BF3 is low. Why it is low, we can explain, because from experiment, we found that the bond length of BF3 is 1.3 angstrom and are significantly shorter than the sum of covalent radii of boron and fluorine. If I add the covalent radii of boron and fluorine, so from here its bond length should be 1.52, but it is coming 1.3. So a large difference is showing that it is not behaving like a single bond. So there is something which contribute to pi bond in BF3. Another result is there. The bond energy is very high, that is equal to 646, which is higher than for any single bond. Like in hydrogen molecule, we know that 434 is bond energy between hydrogen single bond. This is 646, right? So this high value can only be explained by back bonding. So this is BF3 molecule. So this BF3 molecule, we know that it has sp2 hybridization. So ये बोरोन का जो है वो sp2 हाइब्रिडाइज ऑर्बिटल है. So one sp2 hybridized orbital, another sp2 hybridized orbital and the third sp2 hybridized orbital. और ये वाला जो ऑर्बिटल है ये बोरोन का प्योर एटॉमिक ऑर्बिटल है, दैट इज 2pz. आई एम अज्यूमिंग दैट sp2 में अगर px और py और s ऑर्बिटल इंटरमिक्स होके 3 हाइब्रिड ऑर्बिटल फॉर्म कर रहे हैं जो एक दूसरे से 120 एंगल फॉर्म कर रहे हैं, राइट? सो दिस इज हाइब्रिडाइज ऑर्बिटल. एंड देन these fluorine orbitals, p orbitals are forming sigma bond. This is forming sigma bond, right? With so there is an overlapping of sp2 hybridized orbital of boron and pure atomic orbital of fluorine. This is p atomic orbital. So this is sigma bond formation. Now there is an lateral overlapping. This is the end-to-end overlapping to form a sigma bond, but this is lateral overlapping between pure atomic orbital of fluorine and pure atomic orbital of boron. This boron is vacant 2pz or atomic orbital, but this fluorine has fulfilled 2p orbitals. So 2 electrons it have, and there is an overlapping. So 2p pi, right? So this overlapping, because of this overlapping, the electron deficiency of boron is somewhat compensated because of back bonding. And because of that, it is a relatively weak Lewis acid with respect to the other. In case of BCl3, if you discuss the same type of thing, since there is back bonding which will take place from 3p pi atomic orbital of chlorine to 2pz atomic orbital of boron, and the size difference between 2p and 3p atomic orbital will be large. So this overlapping will not that effective. As we move down, the size difference is further going to increase. So the back bonding is going to decrease. And if the back bonding is not there, then the boron is electron deficient. So it will act like a Lewis acid. So we can say that as we move down the group, the Lewis acid behavior of this boron halides are going to increase. The second point is when we are discussing about fluorides, boron fluoride is a gas, it is a covalent molecule, but all other fluorides, because these are metals, so metal and non-metal will combine to form ionic solid. So fluorides of aluminium, gallium, indium, and thallium are ionic and have high melting point. Except BF3, all other halides of boron can completely hydrolyze to boric acid. BF3 is partially hydrolyzed, so this is important. Suppose we are discussing about other than BF3. Suppose I am talking about this BCl3. So this BCl3, we can see here that it has a vacant p or atomic orbital, and because of this vacant p atomic orbital, and the back bonding is less because of 2p pi and 3p pi, so this is electron deficient, and it has leaving group. I can take any one of them is leaving group, right? And this water molecule is nucleophile, so it is nucleophilic substitution reaction. So one nucleophile will attack, and there is a leaving group which is going to leave the system. One is going to attach the system, other is going to leave. So this is taking place simultaneously, so it is a reaction of molecularity too. So two molecules are involved here. So now if I write that when this is happening, transition state, at transition state, this is going to add, and this is slowly removing from the system. And a time will come when this will remove from the system in the form of Cl minus ion. And because of this covalent coordinate bond, if I represent this covalent coordinate bond as a normal bond, then oxygen is giving one electron to boron. And since here when there is a breaking of bond, boron has positive charge. On taking the electron, its charge will disappear. So here oxygen is giving electrons, so oxygen has positive charge. Oxygen is electronegative, it has positive charge. Then what will happen? The shared electrons with hydrogen is shifted more towards oxygen, and this H plus will be released, and this H plus and Cl minus ions will combine to form HCl gas. So after this step, we'll see that this is the molecule BCl2OH. So there is a substitution of Cl by OH. And if we repeat the same step 2 times, then 2 water molecule is added and 2 HCl molecules are removed. And finally, this is converted into boric acid. So in this whole step, the BCl3 molecule is converted into boric acid and 3 molecules of HCl. This is overall reaction. So it is a colorless gas and it reacts with moist air, right? So here water is present in gaseous state, and because of this reaction, HCl will form, which is in gas, and boric acid will form in the form of, boric acid is a solid, so it will exist in the form of solid. Hydrolysis of BCl3, same way we can discuss about BBr3 or Bi3. They have the same complete hydrolysis. But now we are discussing about BF3. Before discussing about BF3, they are saying that if the reaction is carried out in alkaline medium, that was that BCl3 was gas and it is reacting with water gas. Now if BCl3 is dissolved and then it is reacted with NaOH in aqueous state. So what will happen? Again, same thing will happen, that here OH minus will be there. So one molecule of BCl3 will react with 3 molecules of NaOH to form boric acid and 3 molecules of NaCl. Then that boric acid will further react with another molecule of NaOH, like acid-base reaction, to form NaBOH4 and 3 molecules of NaCl. So this is the reaction taking place. In place of moist air, if we take basic medium and react this BCl3 with basic medium, these are the products. Now, if we discuss, this is very important, BF3, it is a colorless toxic gas which gives white fumes with moist air. So BF3 is a gas and it will react with moist air. On reacting with moist air, again here this is nucleophilic substitution reaction whose molecularity is 2. ये जो है वो न्यूक्लियोफाइल है जो इलेक्ट्रॉन डेफिशिएंट केमिकल स्पीसी की तरफ बढ़ रहा है. जब ये बढ़ रहा है तो ये लिविंग ग्रुप इससे निकल रहा है. So both is taking place simultaneously, right? So what will happen when this living group is moving? This is more electronegative, so boron has positive. But if now this oxygen will give electron, there is no charge on boron, but oxygen is giving, so it has positive charge. So here it is. Now F minus is left from the system and this oxygen atom is positively charged. So what will happen? One of the hydrogen will remove in the form of H plus by leaving the electrons, and the charge on oxygen will vanish. And now we can say that H plus and F minus will combine to form HF. And this is addition of one water molecule. When two other water molecules will be added in the same way, there is a formation of boric acid. And now total one HF molecule here and two HF molecule here, total three HF molecules will be formed. So this was the first step. The second step is very fast. This was the rate determining step. So as soon these HF molecules will form, they will further react with BF3. So this reaction is very important. HF molecules will further react with BF3 because they have lone pair of electrons. So it is electron deficient. So this can happen, and there is formation of HBF4 minus, H plus and BF4 minus. So what is happening here? The lone pair is going here, and because of that, this fluorine has positive charge. So this HF bond, again H plus is removed, and this fluorine is attached to form BF4 minus. So H plus and BF4 minus. इसको हम अगर कोऑर्डिनेशन के हिसाब से इसका IUPAC नेम लिखें, so it is known as hydrogen tetrafluoroboric acid, right? And it is a strong acid. So if you see here, whatever the three HF molecule, because one HF molecule will react with one BF3, so three HF molecule will react with three BF3, and this is fast reaction. So overall, what is happening that four molecules of BF3 is reacting, in which only one molecule is reacting with water. So this is known as partial hydrolysis of water. If I write what is the overall reaction, four molecules of BF3 here and one molecule of water. So boric acid is formed. So three molecules of water is there, and there is formation of one molecule of boric acid and three molecules of HBF4, right? So weak acid and strong acid both is formed, and it is not the complete hydrolysis. Only four molecules में से एक ही molecule hydrolyze हुआ है, boric acid बना है. It is 25% hydrolysis. So it is known as partial hydrolysis. So other boron halides are fully hydrolyzed with water, while BF3 is partially hydrolyzed with water. If we discuss the halide of other halides like aluminium chloride and gallium chloride, they are covalent when anhydrous. They are covalent solids when they are anhydrous. However, they dissolve in water to form ions. And people will ask that why it is happening that when they are anhydrous they are covalent, but in water they will form ions. So the reason is the change from covalent to ionics happens because the ions are hydrated and the hydration energy involved exceeds the ionization energy. So it is not the complete steps. Few steps here they have explained that during the formation of these ions, there is formation of aluminium to aluminium plus 3, and then that aluminium plus 3 will combine with water to form aluminium plus 3 in aqueous state. So formation of aluminium to aluminium plus 3 in gaseous state is an endothermic process which required a lot of energy, that is 5137 kilojoule per mole. But aluminium plus 3 when combined with water molecules, this is known as hydration of cation. So the energy releases this value, and this is known as hydration of anion. Energy releases this value. If I write what is the overall hydration energy, then this plus this is greater than this value that they are discussing, that because of high value of hydration energy, these are converted into ions. So the energy is supporting to convert them into ions. So AlCl3 and GaCl3 in solid state, they are bad conductors. There is no conductivity. They are not ionic solids, right? That's why they are covalent. In liquid state, when it is melt, there is no conductivity at all. So because of that, we'll find that AlCl3 and GaCl3 when anhydrous are not ionic, they are covalent. Fifth point, व्हाइट फ्यूम्स अपीयर्स अराउंड द बॉटल. ये एनसीईआरटी का क्वेश्चन है कि अगर किसी बॉटल में AlCl3 रखा है तो व्हाट इज द रीजन दैट व्हाइट फ्यूम्स विल बी देयर. So what will happen that this AlCl3 is electron deficient, right? And when I am saying AlCl3, it should be understand that it is existing in the form of dimer, right? I am talking about dimer. That dimer structure, we know that this is one molecule of AlCl3, this is another molecule of AlCl3. Since the octet is incomplete, this chlorine will give the 2 electrons here. So this bonding is known as bridge bonding, right? So this is the dimeric form. Whenever I am saying AlCl3, basically I am saying this. So white fumes appears around the bottle of anhydrous AlCl3. What is the reason? So because they are electron deficient, so what will happen that anhydrous aluminium is partially hydrolyzed with the atmospheric moisture to liberate HCl gas. Moist HCl appears white in color. So when we are discussing this reaction, this is the reaction. AlCl3 in solid state is reacting with H2O in gaseous state to form AlOH whole thrice, right? So the mechanism is same. It is substitution reaction only, right? That Cl will leave and this OH will go and attach, and H plus and Cl will combine to form HCl. So this HCl, because of this HCl gas, when HCl gas is in touch with water molecule, it will look like a white fume. So because of that, we can see those white fumes, right? Now let us know something about this AlCl3. Crystalline AlCl3 at low temperature, it is a CCP with respect to Cl minus. It is a crystalline solid at low temperature, which is CCP with respect to Cl minus, and cation is present in octahedral void, right? Or we can say that it is CCP with respect to chlorine atom also, I can say. Because of electronegativity difference, we are saying that this minus charge is there. It doesn't mean that it is ionic in nature. And cation is present, aluminium plus 3 ion is present in octahedral void. So now if they can ask a question that what is the coordination number of aluminium plus 3, since it is sitting on octahedral void, I can say that the coordination number of aluminium plus 3 ion is equal to 6. And by using the law, aluminium is surrounded by 3 chloride ions, means the coordination number of aluminium is 3 times that of chlorine. So from here, I can write that the coordination number of chloride ion is equal to 2. Ratio of ions is reverse of ratio of coordination number. Now this AlCl3 solid means it is a dimer. So this dimer on heating, it will melt, and heat of fusion is 35 kilojoule per mole. So in molten state also it is existing in the form of dimer. Solid state also it is dimer, molten state also it is dimer. Again, when we heat it, it will sublime. In gaseous state also it is existing in the form of dimer, and in gaseous state we have found that this angle, we are comparing some angles, right? So if this angle AlClCl is compared with this angle, so this angle is smaller and this angle is bigger, right? And here you can see that this angle is bigger with respect to this. So this is the highest than this and this, and the bond length, this is smaller than this bond length. So the bridging chlorine aluminium bond length is greater than the terminal aluminium chlorine bond length, and the angles are also differ. So aluminium chloride is existing in the form of dimer in solid state, liquid state, and gaseous state. When this gas is heated above up to 350, this dimer is existing. Above 400 degrees Celsius, it is existing in the form of monomer. So AlCl3 अगर कुछ मेंशन ना हो तो हम यही माने कि सॉलिड लिक्विड गैस में up to 350 degrees Celsius it is existing in dimer, right? So above 400 it is exist in the form of monomer, right? AlCl3 will be monomer in gaseous state above 400 degrees Celsius. AlCl3 hydrolyzed, when it is added to water, it will react with water, and since the hydration energy is very high, it will exist in the form of ions. So it exists in this form, right? There are 6 water molecule attached with this aluminium, and there is covalent coordinate bond, and the bond strength of aluminium oxygen bond. Oxygen is giving electron to aluminium. This bond strength is very strong. And because of that, sometimes this whole thing is acting like a acid, right? Sometimes this you can see that it is, we'll discuss some another time, but this can act as an acid. So what we are saying that there is a question in JEE Advanced that when aluminium chloride is added to water, in what form it exists? It is not aluminium plus 3 only and Cl minus. It is aluminium plus 3 in aqueous, and aluminium plus 3 in aqueous is in this form. It is existing in this form, right? So in solid, state, it is converted covalent because on melting it does not show conductivity. Anhydrous AlCl3 is soluble because it is non-polar in nature. If you see the structure here, there is no dipole moment, it will cancel out. So it is non-polar, like dissolved like. So it is soluble in non-polar solvent like alcohol, ethers, and C2H6. And in this, they will exist in the form of dimer. In non-polar solvent, it exists in dimeric form, while in polar solvent like water, it is existing in the form of ions that we are discussing, that hydration energy of aluminium plus 3 and Cl minus ion is greater than the ionization energy of aluminium to aluminium plus 3. So this is the point. Now regarding this, there is another question that anhydrous AlCl3 does not form precipitate with AgNO3 solution, but hydrated AlCl3 gives white precipitate with AgNO3. If you see anhydrous AlCl3, it is covalent. There is no Cl minus ion in anhydrous, but hydrated is existing in the form of Cl minus ion. So it will combine with Ag plus to form AgCl precipitate. So that is the explanation. Another question is, anhydrous AlCl3 cannot be prepared by heating AlCl3.6H2O white, because people can say that suppose we have added AlCl3 to water and this will form. If we allow the water to evaporate, finally this residue will left, right? This is non-volatile, so this will left. So it will exist in the form of AlCl3. I can write like this, but basically it is existing in this form. So they will try to trick you that on heating AlCl3.6H2O, this 6 water of crystallization will go outside and we can obtain AlCl3. But we should remember that there is no water of crystallization in AlCl3.6H2O. They are all inside here and they are attached with covalent coordinate bond. It is a very strong bond. So in order to remove this water, we have to heat very high at 300 degrees Celsius. And at that case, there is no formation of AlCl3. There is formation of Al2O3, HCl gas and H2O gas, because this is 300 degrees Celsius. So heating hydrated aluminium chloride will not form anhydrous aluminium chloride. That is a fixed question by JEE Advanced. In mains also this question is there, right? So I think you understand that there is no water of crystallization here. So on heating, it will convert HCl, it will form HCl, which will go in form of vapor, and H2O will go in form of vapor, and this will be the residue, that is alumina, Al2O3 corundum. It is HCP with respect to anion, and cation is present in octahedral void. First example is the number of species in which the metal ion is present in +1 oxidation state is R. So if we go through the first option, AlF3, fluorine is present in -1 in all of its compound. So I can write here that the oxidation state of aluminium will be +3. In case of the second option, we know that thallium in its compound exists in form of +1, and there is a proof that when we are discussing this I3 minus is basically formed by I2 plus I minus ion. It is not 3 times of I minus ion, it is I2 plus I minus ion. So thallium, we know that it is existing in +1, and I3 is existing in the form of I3 minus. So from there we can say that this thallium is existing in +1 oxidation state. Fluorine is existing in -1. So from there I can say that gallium is existing in +3 oxidation state. Same I3 minus will exist here in form of -1. So this indium is present in +1 oxidation state, and there are proof that gallium, indium, and thallium can exist in +1 oxidation state. CSI3, same way, cesium is alkali metal. It always exists in +1 oxidation state, and this is I3 minus ion. And when we are discussing about this GaCl2, we can say that basically it is apparently, which is looking like this. The actual structure of this is equal to gallium +1 GaCl4. So here if I calculate what is the oxidation state of gallium, this gallium is +1 and this gallium is present in +3 oxidation state. So average oxidation number is +2, but gallium, both gallium atoms is either in +1 or +3 oxidation state. So now they are saying that number of species in which metal ion present in +1. So sixth is the correct option, fifth is correct, fourth is correct, and second is correct. So answer should be 4. 4 should be the answer. Second example, the correct statements about 13th group elements is are boron has highest melting point in its group. Yes, we have discussed that the melting point of boron is around 2000 degrees Celsius because of its crystalline structure, while gallium is a solid at room temperature, but its melting point is 30 degrees Celsius. When we take gallium in our hand, it will melt because body temperature is 37 degrees Celsius. So these two seems to be correct. Today we have discussed about the melting point. Boron is a metal, that is wrong. Boron is definitely a non-metal and the other elements in the group is metals. Boron has the highest ionization energy in its group. Yes, that is correct. Today we have remembered that if we want to write the exact order of ionization enthalpy in boron family, what we'll do that will make an W and will tilt the right hand side, will pull the right hand side leg of that W. So on pulling the right hand side leg, it will be like this. And each corner is corresponding to one atom or element. So here there is boron, then this value will be aluminium, then this is gallium, this is indium and thallium. And we have discussed that the actual order of ionization energy is boron has highest ionization energy, then thallium, and then gallium, and then aluminium, and indium has the lowest ionization energy. So ionization energy of indium is lowest and boron is highest. So D option is correct. So from there we can say that the answer should be A, B, and D. The third example is assertion reason type of question. So there are two statements. Statement 1, the ionization energy of gallium is greater than that of aluminium in 13th group. We can see here that ionization enthalpy of gallium is greater than that of aluminium, and we have explained that why this is happening because of low screening effect of 10d electrons. The ionization energy is going to increase. Here also we can say that 14 electrons screening effect is less, and because of that ionization energy is increasing. So in gallium, due to inability of d electrons to screen, the effective nuclear charge increases. This seems to be correct. So the first statement is true statement and the second statement is also true, and the second statement is the correct explanation. Because of this, the ionization energy of gallium is greater than that of aluminium. So keeping that in mind, we can say that the answer will be A will be answer. Statement 1 is correct, statement 2 is correct. Statement 2 is the correct explanation of statement 1. Next example, again it is assertion reason type of question. Statement 1, this question was asked in JEE 2007. Boron always forms covalent bond. Yes, all the compounds of boron, you will see that boron is always forming a covalent bond. Boron never forms an ionic bond. Boron is always forming a covalent bond. The first statement is true. The second statement, the small size of B plus 3 ions favors formation of covalent bond. Yes, the ionization energy of boron is very high. First ionization energy plus second plus third, if you add all these things, that value is very high, and because of that boron plus 3 does not form. So a small size of boron, and because of that its ionization enthalpy is high and there is no formation of B plus 3 ions. So small size of B plus 3 ions favor formation of covalent bond. This statement is true, and because of high value of ionization energy only, it is not forming ionic bond, it is only forming covalent bond. And high value of ionization energy is because of its smaller size. So statement 1 is true, statement 2 is true, and statement 2 is the true explanation of statement 1. So answer A will come. Next question, again it is asked in JEE advanced 1998, and it is also a some reason type of question. Statement 1, aluminium hydroxide is amphoteric. Yes, aluminium as well as gallium hydroxide both are amphoteric in nature. Second statement is aluminium oxygen and oxygen hydrogen bonds can be broken with equal ease in aluminium hydroxide. So for equal ease, the electronegativity difference between the aluminium and oxygen and hydrogen should be same. If we see the data, the electronegativity of aluminium is 1.5, and this is Pauling electronegativity value. And oxygen is 3.5, hydrogen is 2.1. So by looking the data, we can find out that the difference in electronegativity is 2 here. And the electronegativity difference here is 1.4. So we cannot say that this is breaking evenly, right? So first statement is true statement, and first is true because aluminium hydroxide is amphoteric. Amphoteric means it can react with acid and base. It is nothing to do with ease of breaking of ALO and OH bond, right? Ease of breaking is related to electronegativity difference, and electronegativity difference is differ here. So statement 2 is false, statement 1 is true. So from here we can say that C will be the answer. Statement 1 is correct, but statement 2 is incorrect. C will be the answer. So hope this video is useful to you. Let us meet in the second part of boron family. Thank you.